In this module, we apply frequency response techniques to the design of controllers. Previously, we introduced frequency response methods as a means for analysis. In this module, we will apply these techniques to the design of controllers. Since what we ultimately want to achieve is some sort of response of the system as a function of time, i.e. in the time domain, the first thing that we then need to do is to understand the relationship between a system's time response and its frequency response. Once we've done that, we will then show how to employ Bode plots for the design of controllers, and then finally we will discuss some other goals of a controller, including robustness and optimality. So when we design controllers, we are going to use the Openloop frequency response. So what we want to be able to do is to connect aspects of the system's open loop frequency response to its closed loop time response. So take a look at an open loop Bode plot, for example, and understand how it relates to the closed loop step response. The reason why we want to use the open loop frequency response for design will be explained shortly. So first, let's just try and use our intuition of frequency response to connect the two, and then this will be summarized on the subsequent slide. So let's first think about steady state error. For a type 0 system and step reference, E steady state depends on the DC gain, and it has some sort of form like this. So recalling this sort of expression which we derived earlier in a previous module, think about what aspect of the frequency response plot would tell us about a system's steady state error. What the steady state error is for a step input, for example. DC gain corresponds to a constant input, and a constant input basically has a very small frequency, a frequency of 0, if you will. And so if we look at a system's frequency response, small frequencies are to the left on the Bode plot. So this region over here gives an indication of a system's DC gain, and in turn tells us about a system's steady state performance. So say at steady state. Now let's think about what might tell us about a system's speed of response. For example, its peak time, how quickly it rises or reacts. So looking at the frequency response plot, what we can see is that most typical systems, they can track slowly moving inputs well. So at low frequencies, a system tends to have a magnitude that's 0 dBs or greater, meaning you put in a sinusoidal input and the output is either equal in magnitude or it's amplified. As you make the input faster and faster, have a higher frequency, oftentimes the system can't keep up. And so what it does is it starts to attenuate the input. So you could sort of imagine, let's say we had a first order system. And so if we put in a step input and then we turn the step off, and then we turn the step on, and then we turn the step off. If we do it at a very slow frequency, the system has a lot of time to react, and so it can get very close to its steady state value. But if we're switching that step input on and off very quickly, then the system doesn't have very much time to react, and you get in essence a very small amplitude output. And so that's typical. So if our system is fast, it can track fast changing inputs well, but if our system is slow, then it can't react very quickly and the output ends up having a very small amplitude. So out here, high frequencies tell us about speed. How fast of an input our system can track tells us the speed. If the system can track a very high frequency sinusoid, then it's a fast system. If it can't, then it's slow. Now let's think about what would relate to overshoot or oscillation. So one thing that you might recognize is basically how big a system's resonance is. If it has a large resonance, that indicates that the system will have more overshoot. Furthermore, if a system overshoots a lot, it tends to indicate that it's not very stable. And so we can also look at stability margins, in particular phase margin. So these are three sort of basic things or areas to look at to tell us about steady state behavior, speed of response, and overshoot/stability. And they're further summarized on the next slide. Okay. So in terms of steady state performance, we need to look at low frequencies because a constant input corresponds to a frequency of basically 0. So larger gain at DC indicates reduced steady state error. And this is true no matter the type of the system. But if we had a type 0 system, then the slope at low frequencies is flat, and the DC gain is recognized by the magnitude at those low frequencies. If we have a type 1 or a type 2 system, the magnitude at low frequencies won't be flat, it'll be sloped, and the slope will indicate the system type. So if we have a slope that decays at 20 dBs per decade, then that tells us we have a type 1 system, we have one integrator. If it decays at minus 40 dBs per decade, then we have two integrators, we're a type 2 system. So that also indicates the sort of steady state behavior of the system. And even if we had a type 1 system, if it was raised, if the magnitude at which the plot crossed 1 radian per second, for example, was higher, then that would indicate that the system could track a ramp with less error. So larger DC gain or larger magnitude at low frequencies in general indicates steady state performance. In terms of transient performance, a smaller resonant peak and a larger phase margin indicates smaller overshoot and that the system is more stable. Speed of response is indicated by a larger gain crossover frequency. So gain crossover frequency is the frequency at which the magnitude goes from above 0 dBs to below 0 dBs. So that's basically the frequency at which the system goes from amplifying an input to attenuating an input. And a system attenuating an input means basically that it can't keep up, that it's not fast enough to track an input of that speed. And so gain crossover frequency is a good indication of a system's speed. Now that we understand the relationship between a system's frequency response and its time response, we now know how to alter a system's frequency response in order to achieve a desired time response. And we'll use that to design controllers in the following way. So first, we'll analyze the time response behavior of a system to determine its deficiencies. Since ultimately what we care about is how the system behaves in the time domain, That's what we will use to determine, is the system too slow, does it overshoot too much, whatever. We will then plot the system's open loop frequency response. Then we'll add a controller to change the shape of the frequency response plot to cause a corresponding change in the system's time response behavior. Make it faster, make it overshoot less, etc. We, in particular, are going to use Bode plots, and we're going to use the open loop. We're going to use Bode plots, and we're going to use the open loop frequency response. And the reason that we do that is because of the property of Bode plots. The Bode plot of the plant will literally add to the Bode plot of the controller. For example, our open loop might be something like this: a controller in series with a plant. And since the transfer functions multiply, their Bode plots add. And we remember this from the way that we sketch Bode plots by component. If we had something like a Nyquist plot, we don't get that nice additive behavior. So it's harder to determine the type of controller that we need to reshape the system's frequency response. Furthermore, if we used a closed loop system, which perhaps has a transfer function something like this, the addition of a controller wouldn't just add to the Bode plot of the plant. You don't get that nice sort of linear relationship. So employing Bode plots with the open loop frequency response is a very natural way and an easy way to design controllers. One thing that you have to be a little bit careful about is that a system's frequency response, its Bode plot, the magnitude and the phase depend on one another. So if, for example, you're trying to achieve a certain steady state error by changing the DC gain, or you're trying to achieve a certain speed of response by changing the gain crossover frequency, you may adversely affect the system's phase margin and therefore its overshoot. And so because of that, often this process is iterative. You sort of have these competing goals that are always fighting against one another. Furthermore, this relationship between the time response of a system and its frequency response at this point is very qualitative. If we had a canonical system, we could define explicit relationships between time response and frequency response. But in our case, and when you have sort of non-canonical systems, you won't have an exact relationship between the time response and the frequency response. So that will also force you to iterate. You'll sort of have a sense of whether or not this change will make the system faster or slower, but you don't necessarily know by how much. Okay. So let's go through a simple example. And so the first step is to analyze a system's time response. So let's say that we look at a system step response and we determine that this behavior isn't good enough. Let's say we've decided that this is too slow, that it has too much overshoot, and that the steady state error is too large. So basically we need to improve everything about the time response. The second step is then to plot the system's open loop Bode plot. Looking at the open loop Bode plot, we then get a sense of how we need to reshape it in order to address these deficiencies we identified from the time response. So since it's too slow, think about how we would want to change the open loop frequency response to make it faster. Okay, so we recall that gain crossover frequency is an indication of speed of response. So we want to push the gain crossover frequency out to a higher frequency. Okay. Now let's look at the overshoot requirement. We want to bring the overshoot down. How do we do that? So one thing to look at is, we may want to bring down this resonant peak. Another thing to look at is the system's phase margin. So the phase margin is how far above minus 180 degrees the phase is at the gain crossover frequency. So that gives us an indication of phase margin and gives us an indication of overshoot. So we want to increase the phase margin. We want to bring the system up. And in particular, we want to bring it up at the system's new gain crossover frequency. So it may not be at this location any longer. It may be pushed out. And then finally, we want to improve the system's steady state error. We want to reduce the steady state error. So think about how we might achieve that. So steady state behavior is indicated by the system's sort of DC behavior, its behavior at low frequencies, where this specifically is the DC gain. So in this case, its magnitude at low frequencies is 0 dBs, which corresponds to a magnitude of 1. So we want to take this DC gain and we want to push it up. So we want to increase the magnitude at low frequencies. The way that we're going to achieve these changes, one option would be to redesign the plant. So that's one option. The other option is to add control. And so that's what we'll do in step 3. So we basically want to push up the DC gain, we want to push out the gain crossover frequency, and we want to bump up the phase margin. And you could think about what the frequency response plot of different controllers that we've used might be. Think about what it would look like with a PD controller or a PI controller. I'm going to go ahead and propose a controller that we haven't heard about yet. It's called a lead compensator. So we're going to try a lead compensator. I'm just going to give it to you, but we'll discuss it further as we go along in the course. The structure of a lead compensator is basically that it has a single zero, so we'll give it some gain K, has a single zero and a single pole. But the zero is smaller than the pole. So you could almost think of it as if the zero is dominating a little bit. So let's go ahead and plot the Bode plot of this controller to get a sense of how it will affect our system when we add it to the plant. In order to plot this, I'm going to go ahead and change the transfer function into Bode form, so that the zero has a form TS plus 1, the pole has a form TS plus 1. So in order to achieve that, I'll factor out a Z out of the numerator, and I'll factor out a P out of the denominator, and I'll be left with 1 over Z times S plus 1 divided by 1 over P times S plus 1. And now I'll go ahead and draw the Bode plot, where we'll have a magnitude plot versus frequency and a phase plot versus frequency. Okay. In general, the way that we could plot the Bode plot is as we've done before. We can plot it component by component. So plot the Bode plot of a gain, plot it for a simple zero, plot it for a simple pole, and then add them up. I'm going to go ahead and do it all at once. If you don't exactly follow what I'm doing, you can always do it yourself, component by component, then add them. So looking at this, the system has some DC gain corresponding to K and Z over P. So let's say that's 0 dBs, and there'll be some gain. If we want to bump up the DC gain, if we want to bump up the magnitude at low frequencies, what must need to be true about K times Z over P? Well, basically this needs to have a magnitude greater than 0 dBs, or greater than 1. And if we do that, then we'll have a positive magnitude at low frequencies as we desire. We then have a pole and a zero, and in general, zeros cause the slope to go up at 20 dBs per decade, and poles cause the slope to go down at 0 dBs per decade. Since the zero is smaller, that means that we will hit it first. You know, the break frequency for the zero is 1 over t, where t is 1 over z. So the break frequency for the zero will occur at z, and since that's smaller than p, we'll hit that first. So then we'll start to go up at 20 dBs per decade, and we'll continue to go up at 20 dBs per decade until we hit the pole. And then when the pole comes in, the pole adds in a slope of minus 20 dBs per decade. And so in essence, the positive slope from the zero and the negative slope from the pole cancel, and the magnitude plot levels off again. And we get a shape like that for the magnitude plot. If we consider the phase, again, zeros, the phase starts off at 0 and then it moves up to plus 90. With a pole, the phase starts at 0 and it moves down to minus 90. Since the 0 is smaller, we'll hit that first, and in particular we approximate it as beginning 1 decade early. So at 0.1 Z, we go from flat, and then we ramp up, and eventually we'll either stop at 90, which will happen, we approximate as happening 1 decade after the break, so at 10 times Z, or it will level off once the pole comes in. So once the pole comes in, the phase is sloping up because of the zero, the phase is sloping down because of the pole, and it approximately cancels. So it'll eventually level off. Then it will start going down again, either when the zero runs out or the pole comes in. And ultimately it'll stop going down 1 decade after the pole. And we know that it will stop going down at 0 degrees. So it starts at low frequencies at 0 degrees, and at high frequencies it goes back to 0 degrees. And we know that the behavior is like that because at high frequencies the zero goes to positive 90 degrees and the pole goes to negative 90 degrees. And so if you sum those two, 90 plus negative 90 is 0. So ultimately, this is the shape of the open loop Bode plot, the open loop frequency response of our controller, our lead compensator. And if we put it in series with our plant, then the new Bode plot, or the Bode plot of the controller together with the plant, is just simply the sum of the controller's Bode plot and the plant's Bode plot. So if we do this, at low frequencies, we'll have a positive magnitude. So we'll shift this up by adding the two together. And let's say we don't have the zero come in for a while, so it just adds a constant amount. And then let's say that we hit the zero somewhere in this area. Then the magnitude goes up and we're adding even more at high frequencies. So if we're adding 5 dBs at low frequencies, maybe we're adding 10 or 20 dBs at high frequencies, and there's some transition period. Okay, so that red line is the two together. And we do the same thing with the phase. So at low frequencies, we're adding in 0 degrees, so it's almost unchanged. And then when the 0 comes in, we get a bump in phase. And then eventually at high frequencies, it goes back down to 0 degrees. So let's say we get something like that. And so by the addition of our controller to our plant, you can see that we meet all of our goals. So we get more DC gain, which helps reduce the steady state error. The gain crossover frequency is where we cross 0 decibels. So we push that out to a higher frequency. So larger gain crossover, call it omega C. And this was where our old crossover frequency was. So that was our old phase margin. This is our new crossover frequency. We got a little bit more phase margin to help the overshoot. Again, this is an iterative process, so if that's not sufficient, then we could try to add more, or we could try and change the location of the pole and the 0 of our controller. So there's a compensator that will achieve all the goals we were trying to achieve. It turns out that a lead compensator achieves similar goals to a PD compensator, PD controller, where if you recall, a PD controller has a derivative term, it has a constant multiplying the derivative of the error, and then it has a proportional term, which is a constant just multiplying the error. And you can also recall that this has the form of a gain and a 0. So let's think about how the Bode plot of a PD controller is different from the Bode plot of a lead compensator. In particular, let's look at the magnitude plot. So what would the magnitude plot of the PD compensator look like? So again, we have a gain out front. Here it's just K, up here it was K times Z divided by P. And we would want that to be greater than 1, to be above 0 dBs to help the DC gain. And then we have a 0 that comes in, and then the slope starts going up at 20 dBs per decade. But there's no pole, so it never stops going up. So it continues to slope up and goes to higher and higher magnitudes as frequency gets larger. So comparing these two, comparing the magnitude plot of a PD compensator to the magnitude plot of a lead compensator, can you see any issues, or can you make a guess as to which one is preferable? And so what you see is that the PD tends to amplify high frequencies more than the lead. The lead levels off. The PD keeps going. So it amplifies high frequencies, which is an issue because noise tends to be high frequency. Okay. And so this is something that we've discussed previously about differentiation, and we can see it explicitly in the Bode diagram, in the frequency response plot. In the previous example, we saw that we employed the open loop frequency response for performing our controller design. This is true in general. We also saw in previous modules that we use the open loop frequency response for analysis, in particular for looking at stability margins. Phase margin and gain margin are both found from the open loop frequency response plot. An exception to this, a property where instead of using the open loop, so for most things in this course we'll use the open loop frequency response, but one exception is called bandwidth, and it uses the closed loop frequency response. In particular, it's a measure of the system's closed loop speed of response. Previously, we had used the gain crossover frequency, which we found from the open loop frequency response, to measure the system's speed of response, and these two are related. Bandwidth is defined as the frequency at which the closed loop magnitude plot drops -3 decibels below the DC magnitude. In a similar way to why we use gain crossover frequency, we can see that bandwidth is a measure of speed of response because it captures the frequency at which the system starts to attenuate an input. In other words, it captures the frequency at which the system is no longer able to keep up with the input. Bandwidth in general is a common property that's used even outside of control systems. Within control systems, generally the DC magnitude of a closed loop system will be 0 dBs. We put in some input, we want the output to match the input, so we want it to have a scaling of 1 or a magnitude of 0 decibels. In other situations, for example, looking at an amplifier or whatever, it's not necessarily desired that the magnitude be 0 dBs. It might be, 100 gain amplifier or something. And so there we wish to know at which point is the amplifier no longer able to keep up, where its output is no longer able to maintain that 100 gain. We won't talk about bandwidth too much in this class, but I thought we would introduce it because it's such a prevalent property. At this point, I'd now like to compare our frequency response approach to analysis and design to the previous types of analysis and design we've been employing, in particular time response analysis and the use of pole placement controller design, or the root locus for placing the closed loop poles. And so an advantage of this frequency response approach is, one, that it's a richer source of information than, say, a system step response. So it captures the system's response to inputs of a whole range of frequencies, all the way from a steady state input to very fast changing inputs, whereas a step response explicitly shows the response only to a single input, though it does give some indication of how it might respond to other inputs. Furthermore, the frequency response tells us a lot more than just the poles do. So for example, if we just looked at the poles of a transfer function, that wouldn't tell us anything about steady state behavior, about the DC gain, whereas a frequency response plot does. So placing the poles all by itself is not enough to achieve a certain steady state requirement, but designing using a frequency response plot does enable us to do that. Furthermore, frequency response plots settle ambiguities from the root locus. So the root locus shows us the closed loop pole locations, so it doesn't even necessarily show us what the closed loop zeros are. So it's hard to see the effect. With the root locus, it's also hard to tell the contribution of different poles if there isn't a dominant 1 or 2 poles. So if you had 4 poles that were in the same basic range of speed of response, it would be hard to know the contribution of each. It would also be hard to know the contribution of a pole if it's near a zero. So we understand this concept of a pole-zero cancellation and how they reduce the effect of one another, but how much do they reduce the effect? That you can't really see from the root locus, but you can see it from the frequency response. And I'll try and exemplify that as we go through more examples. The frequency response approach to experimental derivation is also advantageous because you can see the effect of higher order poles. With the step response you kind of just see the effect of the dominant poles. So you can see the effect of non-dominant poles, you can see the effect of zeros, and you can see the pole-zero cancellations. So every time there's a pole, every time there's a zero, you can see exactly how the magnitude changes, how the phase changes, and in turn you see the effect on DC gain, gain crossover frequency, phase margin, all of these things that tell us about a system's time response. The advantage of a time response approach or a pole placement approach is that it gives us results specifically in the time domain, which is ultimately what we want. In particular, if we have a canonical system, then we know precisely what the time response will look like based on a placement of the poles or based on an analysis of the transfer function. Whereas with a frequency response approach, often we're sort of dealing with a qualitative relationship between what we observe with the frequency response and what it means in terms of the system's time response. So far in this course, we've primarily been concerned with achieving the least amount of error possible. If we look at two different controllers, or we try and design a controller, we try to achieve a certain level of error, either steady state error or a certain transient performance which indicates how quickly we drive down the error. So, the transient sort of tells us what the immediate error is, and the steady state tells us what the error is eventually. Things like settling time tells us how fast we drive down the error. Peak time tells us how quickly we get to our peak. There are, however, other considerations besides just how much error does the system achieve and how quickly does it get there. For example, we might be concerned with how much control effort is required, how much force or torque needs to be applied by our controller, and that has implications for cost and efficiency. Also, we may be concerned with the robustness of the system, robustness to undesired inputs or to uncertainty in our system. In the particular case of automotive applications, some things that we might be concerned with are emissions, driver comfort, driver safety, sort of the safety of our components, of our system. And so these are all what I would sort of classify as sort of more advanced topics dealing with these. But at this point we'll go ahead and discuss them at least at a qualitative level, because they are so important, and we can use a lot of the tools that we've learned to sort of understand, at least qualitatively, some of these aspects with regard to our systems. Ultimately, we would like to find the best controller we can, which we will define as the controller being optimal. And so what defines the best controller depends on your specific goals. You sort of have to define a measure of what is best in terms of a balance of these different competing goals. Minimizing error, minimizing how much control is used, making the system as robust as it can be. This is another thing that we will talk about sort of more at a qualitative level. Okay. So first let's discuss control effort. Large control effort often means more cost in terms of the implementation and operation of a controller. Specifically, it often means more power or fuel is required. If your engine needs to generate more torque, it may take more fuel. If your motor needs to generate more torque, it may require more electricity. And so that fuel, that electricity costs money in a sense. And so requiring more control effort means that the operation of that controller costs more money. If we require a large peak control effort, then that means we also need a larger actuator, a larger engine, a larger motor, which also corresponds to higher cost. A very basic way to sort of indicate how much control effort is required is to look at the speed of response. So if we are able to get away with a slower response, then oftentimes that means that we'll require less control effort. If we have to get there very fast, then we need a big force, we need a big effort. If we can get there slowly, then it requires less force, less effort. Another goal that we mentioned is robustness. So we want to know how well does the system perform in the presence of sort of undesired inputs and undesired model uncertainty. So measurement noise and disturbances are examples of unwanted inputs, and we want them to not adversely affect the response of our system, the behavior of our system. In essence, we want our system to not react to noise and disturbances. We also want to be robust to uncertainties in our model. So we've designed our controller based on some model of the plant, and we achieve a certain level of performance. We want that performance to not degrade if it turns out that the actual system is different than our model. So if there's a certain amount of uncertainty in the mass of a vehicle or the inductance of a motor, we want changes in those parameters to not have a large effect on the performance of the system, its speed, its overshoot, its steady state error, etc. And we also want the system to be robust to time delays. And so this isn't something we've talked about much, but we will talk about it in a little bit in more detail. But in essence, if we're using a sensor or we're using some information and it's delayed such that it's old by the time our controller tries to employ it, we want our system to still perform well. We don't want the delay in that information to degrade performance, to cause us to go unstable even. In general, there is a trade-off between robustness to these different sources. As is always the case, we generally cannot achieve all of our goals simultaneously. For example, we may not be able to make our system robust to both noise and disturbances at the same time. And we'll show a little example of this on the next slide. So let's consider this multiple input, multiple output system, this MIMO system. And we have three different external inputs. We have the reference R, we have a disturbance D, and we have noise N. And we want to react to these three different inputs in different ways. In particular, we want to attenuate disturbances and noise. We don't want to react to those inputs, those undesired inputs, but we don't want to attenuate the reference, the command that we're actually trying to follow. So let's go ahead and take a look at the closed loop transfer function for each of these three inputs to an output of y to try and better understand this situation. So for an input of r and an output of y, we have a negative feedback loop, and we can use our shorthand rule, forward over 1 plus loop. In this case, the forward path includes the controller and the plant, so the forward path is c times p. The loop is also c times p because we have a unity feedback system. Therefore, the transfer function from r to y is c times p divided by the quantity 1 plus c times p. if we look at the disturbance, we still have a negative feedback system. It's just that the disturbance enters in a different location. So the forward path in that case, from an input of D to an output of Y, the only thing that's in the forward path is P. But the loop itself is the same. So the closed loop transfer function from D to Y is P divided by the quantity 1 plus C times P. P is the forward path, C times P is the loop. Then if we look at an input of noise, and you look at the path from the noise to the output, the only thing that it includes is C and P, but you will also notice that this input passes through a summing junction with a negative sign. And since we handle one input at a time, i.e. we treat R as if it were equal to 0, when n passes through this negative sign, it's as if it's 0 minus n. So it's as if we're multiplying by a negative 1 when we go in the forward path. The loop, however, will be the same, and so then you see what we achieve. The closed loop transfer function from n to y is negative C times P divided by the quantity 1 plus C times P. So looking at these three transfer functions, you'll notice a few things. One, all three transfer functions have the exact same denominator. So that means the closed loop system for each of those three inputs has the same poles, presuming no pole zero cancellations. In fact, the transfer function from R to Y and the transfer function from N to Y are identical, except for the negative sign. And so right away you can see that if you desire to attenuate noise, you can't do that without also attenuating the reference. So here's an example of this limitation. So here you can see that the transfer function from R to Y is equal to the transfer function from N to Y, just with opposite sign. These two transfer functions are also related to the third transfer function, the transfer function from the disturbance to the output, as shown here. And so the takeaway is that these transfer functions are not independent. So if you do something in order to, let's say, attenuate the disturbance, you may adversely affect the system's response to noise or the system's response to the reference. Going a little bit deeper, let's go ahead and attempt to design a controller to attenuate noise and to attenuate disturbances. So for example, if we made the magnitude of our controller large, if we made C large, then for a disturbance, this magnitude of C is getting large, and let's say the magnitude of the plant, the process, is staying the same, then we have something that's getting very large being divided into something that's staying the same, and so the magnitude of the response of the output to that disturbance will get smaller and smaller and smaller. And in the limit you could make it approach 0. So making the magnitude of the controller large would make the system attenuate the disturbance completely. If we did that, however, what would the effect be on the system's response to noise? So if we made C very large, then this quantity would get large and it would dwarf the 1. And so you would get something of a large magnitude divided by something of an almost identically large magnitude. And so the magnitude of that transfer function would approach 1, since magnitude doesn't depend on sign. So here we see that we were able to attenuate the disturbance, but we weren't able to attenuate the noise. In fact, the noise is not attenuated at all. Its phase is shifted 180 degrees, but that doesn't really matter. What matters is that the amplitude of the noise directly affects the output. It's not attenuated at all. So let's try the other approach now. Let's try to make the magnitude of the controller small, make it approach 0. If we do that, looking at the transfer function from D to Y, we make the magnitude of C very small, then the magnitude of this quantity will be small, and we'll basically approach P divided by 1. And so as we do that, the closed loop transfer function from D to Y approaches the transfer function of the plant by itself. So what that means is, however the plant responds to certain inputs of a certain frequency, that's exactly how the closed loop will respond to disturbances. If we look at the effect on noise, if we make the magnitude of C small, then we get a small magnitude in the numerator, we get a small magnitude here, so we'll have something that's getting very small divided by something that's basically 1, and so the smaller we make C, the closer that transfer function becomes to 0. By inspection, we can see that making the magnitude of the controller small is good for noise, but not good for the disturbance. And if we make the magnitude of the controller large, that's good for the disturbance, but it's bad for noise. And so the lesson is, we can't attenuate both noise and disturbances at the same time, or at least not necessarily. So what do we do? Well, one solution is that we can rely on the fact that our systems respond differently to different frequencies. And so we can sort of take advantage of this and make the system attenuate noise in one frequency region and make it attenuate disturbances in a different frequency region. Specifically, we will attenuate noise at high frequencies, because noise tends to be high frequency, and we will attenuate disturbances at low frequencies, because disturbances often change slowly. So you could imagine, for a cruise control example, that a change in grade or a change in the mass of the vehicle will change very slowly, or a wind gust, the dynamics of that will be much slower than the frequency of electrical noise, for example. And so this is a strategy that will work well in many instances. And based on the previous slide, we saw that in order to attenuate noise, we want our controller to have small magnitude, and in order to attenuate disturbances, we want our controller to have large magnitude. So that means that we're going to try and achieve an open loop frequency response plot that has high gain at low frequencies, to attenuate disturbances, and small gain at high frequencies to attenuate noise. This sort of approach is also advantageous because we tend to have the most uncertainty at high frequencies. And we saw this a little bit when we had that example where we did the system identification of a power converter. The model was really jumping around at high frequencies, and you could imagine that might be the case because it's difficult to measure the phase very accurately when you're dealing with large frequencies. If you have a very small period, a small time instant is a very large percentage of the cycle. And so by attenuating the high frequencies, maybe we don't know what the model is doing very well, but if we attenuate it, then we don't have to worry about it as much. We're not sure what it's doing, but we're just going to attenuate it so that we don't have to worry about it. In addition to noise and disturbances and model uncertainty, another thing that we wish our system to be robust to is time delays. And so most real systems have delay in them. Examples include when the sensor and the actuator aren't in the same location. For example, you can imagine if you had a sensor in your exhaust, for emissions or whatever, and you're using that sensor to control the engine. Well, that sensor is downstream of the engine. In essence, there was the combustion process, the gases are expelled, and a little time later they reach the exhaust. And so if you're using that sensor information to control the engine, you're in essence using old or delayed information. Since we deal with digital systems these days, a lot of controllers are implemented on digital computers. Sensor readings are sampled at discrete intervals of time. So if you're sampling a sensor every 10 milliseconds, by the time that you reach the end of that sampling period, your sensor measurement is 10 milliseconds old. Or if you're doing some very complex calculation, you're inverting a 100 by 100 matrix or something, the time that it takes to do that computation means that once you actually apply the control, it's now based on old information because it took so much time for you to do the computation. Another example that's especially common within automotive applications is network delays. So if you have a wheel speed sensor and you need to send that information on the CAN to the powertrain ECU, then by the time it gets across the CAN, it will again be delayed. And so here's sort of the picture. This is the true function of whatever it is that you're reading, the wheel speed or whatever, and it's been delayed, so by the time your controller actually gets to use it, it's old. We discussed this property earlier in this semester, and you probably don't recall it, but delay in the time domain is multiplication by an exponential in the Laplace domain. And this is sort of the inverse. Delay in the Laplace domain is multiplication by an exponential in the time domain. If you don't remember this property, that's fine. It's not a big deal. But if we want to consider the frequency response of a pure time delay, something like this, then the way that we do it is we substitute j omega for s. And then we can use Euler's identity to rewrite that exponential with j omega substituted for s in terms of a sine and a cosine. So this is our pure time delay with j omega substituted for s. We can then look at the magnitude and phase of this complex number, where magnitude is determined using the Pythagorean theorem, a squared plus b squared equals c squared. So these are the two legs, the real part and the imaginary part, and the hypotenuse is the magnitude. And if you recall back to high school algebra, you may remember a trig identity that sine squared plus cosine squared equals 1. And so when you square these two and you take the square root, you get that the magnitude is 1. Furthermore, you can look at the phase, where the phase is equal to the inverse tangent of the imaginary part divided by the real part, so opposite over adjacent. Since sine divided by cosine is a tangent, inverse tangent of a tangent cancels out, and since it's an odd function, the negative sign comes out front. Tangent of -1 is equal to negative tangent of 1. And so that we get that the phase is equal to minus omega t, where t is the time delay. So this is the magnitude, and this is the phase. And so what you see is the magnitude of a pure time delay is always equal to 1, no matter the value of omega, no matter the frequency of the input. However, the phase gets more and more negative as omega is increased. So t is the time delay, it's just a constant, but you increase the frequency of the input and you get more and more phase lag. So when you add this to your system, you add this pure time delay to the frequency response of your system, it doesn't affect the magnitude plot, but it does add phase lag. Okay? It doesn't affect the magnitude plot because a magnitude of 1 doesn't scale anything. The input is the same as the output. And if you converted it to decibels, that means that the magnitude of a pure time delay always has a magnitude of 0 decibels. And since with the product of two components their Bode diagrams add, you're essentially adding 0 dBs everywhere to the magnitude plot. With the phase plot, however, you're subtracting more phase. And since the phase plot is in degrees, we convert the previous expression into degrees from radians, and we get an example like this. So here, the blue line is the frequency response of the system by itself. The red line is the frequency response of the system with delay. So it's basically the frequency response of the system added to the frequency response of the pure time delay. So with the magnitude plot, it's unchanged because we're adding 0 decibels everywhere. But here, with the phase of the pure time delay, we can see that for small omega, the phase is small. You can see that here. At low frequencies, when you add the pure time delay to the phase of the original system, you're not adding a very large number, you're basically adding 0. But as omega gets larger, you're adding more and more and more phase lag. And what you see happens is it basically eats away at the phase margin. So you can see originally, if this is the gain crossover frequency, the blue line had that much phase margin. You add in the delay, and now you have less phase margin. You add more delay, you eat that away further, and eventually you'll destabilize the system. The phase margin will become negative and your system is unstable. It sort of makes sense that the phase lag would get larger as frequency gets larger. And that's because our time delay is a constant, but as our frequency gets faster and faster, the period gets smaller and smaller. And so this time delay t becomes a larger percentage of the period. It becomes a larger percentage of the cycle time. So that's the effective pure time delay, and we want to make sure that we have enough phase margin that when we consider the delay, we don't become unstable. So this brings us to the conclusion of this module. In this module, we first discussed the relationship between a system's time response and its frequency response. And so this is very important. But there are 3 things we can look at. 1, the DC gain of the frequency response indicates the steady state behavior of the time response. So looking at the Bode plot at small frequencies, the phase margin and resonant peak of the frequency response indicate the time response is overshoot. And the gain crossover frequency from the frequency response plot indicates the speed of response of the system. We also discussed how to design controllers, and we saw that we used the Openloop Bode plot because it allows us to just add the controller Bode plot to the plant Bode plot. So it's very easy to anticipate the shape of controller we need to reshape the Openloop frequency response. And we also discussed at a qualitative level some sort of more advanced considerations, things like control effort and robustness.